Today I'll describe a very simple test instrument that can be very useful for those who like building and experimenting with radio circuits. It is a Q meter. Now, what is a Q meter? Well, a Q meter measures the quality of inductors, such as often used in tuned circuits. And if you are willing to do a bit of mathematics, you can also use it as a crude inductance measure as well. It's very, very simple, only a few parts, but you do need a transceiver, a low power CW transmitter to drive it, and you also need a digital multimeter. Or if you want, you can make the unit self-contained and add a panel meter, which I've got here just below this piece of paper, but it's not in use, so I won't talk about that today. Inductors come in all different shapes and sizes, large and small, and although you may have two inductors with the same inductance, there's other factors that may make them less or more suitable for your application. One of those critical factors is Q. Basically, Q, you can say, means quality, and a high Q coil will tune sharper and have a lower loss than a low Q coil. Let's supposing that you've got frequency along here, and here is relative signal strength. You've got the coil in a tuned circuit, say a bandpass filter, and all other things being equal, a low Q coil will have more loss and be less sharp in tuning than a high Q coil. In most cases, you want to go for a reasonably high Q of coil, especially in circuits like receiver front ends and crystal sets, because a high Q means less loss and better selectivity. A low Q front end might not be very good at rejecting extraneous signals, although there can be applications where you do need low Q. But anyway, with this instrument, what you can do is you can test various coils and have comparisons between low and high Q. This one's not particularly accurately calibrated, so you wouldn't get much better than a relative indication. But it's very simple inside, so we'll take a look in it in a moment. But before, we'll just get out the circuit. This is the circuit in its simplest form. You've got a bit of RF from a QRP HF transceiver. I use my FT817. And the benefit of that is that operates on a variety of frequency bands. And depending on the coil, you might be doing the tests at 1.8 megahertz or 7 megahertz, maybe 50 megahertz. Anyway, you've got a large choice there of frequencies, which is very handy. Then you've got a 50 ohm dummy load, which in this case is a collection of parallel resistors, totaling 50 ohm. Reason why the resistors are in parallel, that increases their power rating. I've got 3 resistors there, so you've got 50 ohms. You've got a much lower resistance here. In total, it's 0.2 of an ohm. It's all the resistors I had. They're a higher value, all in parallel. Here is our unknown inductor, and here is a wide range variable capacitor, 15 to 450 picofarad. You might recognize this circuit as an L match, and it's configured exactly the same. Here is the low impedance side. This is where the transmitter is connected. And here, this is what's often called a gimmick capacitor. If you've got a fixed capacitor of about 1 picofarad, you could use that instead. But all I've got here is just a few turns of insulated wire. So there's a small amount of capacitance there, and that taps off the RF. And this is at a high impedance, so it's high voltage, low current. And that couples it through to these diodes that converts it to DC. And we've got here a very high value of resistor, 10 megohm, so there's very little loading on this, so it's very, very high impedance. Anyway, that goes to a digital voltmeter or multimeter on a volt setting. How do we use this? Let's say you wanted to do your tests at around 7 megahertz. Now, the FT817 will transmit, I think, from 7 to 7.5 megahertz. Maybe it's only 7.3, but anyway, put it in the middle of that band, like 7.2 megahertz as your center frequency. Put in your unknown coil, adjust the variable capacitor, and you'll see the voltage reading on this go up. It's better to use an analog meter if you can. You could use an amplifier, a DC amplifier circuit to do that, but it will work with a digital meter. Anyway, you adjust this for a peak reading. That's at your center frequency, and then what you do is you adjust the frequency. This is on CW, by the way, so you're applying just a constant carrier. You adjust the frequency, you go up, and then you make a note of where you are at 0.7 of the indicated voltage you got. So when you were doing the peaking before, just write down the voltage, multiply it by 0.7, adjust the frequency up until it gets to the point of it will drop off from the peak. When it's at 0.7, then make a note of that, and then tune back down with your carrier still applied, and you'll find a lower frequency where it drops off to 0.7 on the low side. In other words, here is your peak at the center frequency. About here might be, or it's more like nearer to about here, is 0.7. Just make a note of the low frequency and the high frequency and take the difference between them. So let's say this is 7.2 megahertz. You've got it at 70% at 7.3, and then you go down here and it's 7.1. So you've got 200 kilohertz here, where the output is 70% or more of your maximum. So that's 0.2 megahertz. Now your Q is, you've got 7.2 megahertz, that's your center frequency. 7.2 divided by 0.2, and that is, well, if you divide something by 0.2, you're multiplying it by 5. So 7 times 5 is 35. So it's 36, which is a pretty low quality coil. It's just a hypothetical example. And then you do that for different types of coils. You may need to use different frequencies, but it's the same principle. Your center frequency is there, and this is the range between your where it's dropped down to 70% either side. I should give you a close-up of what I did for the dial. This knob, it's a metal knob, which isn't ideal because it is screwed via a grub screw, you can see it there, straight to the shaft of the variable capacitor. It would be better if you had a plastic knob so there's no hand capacitance effects when you're touching it. The other thing is the pointer. I'll just go into a bit closer, and it is just a cable tie. And right at the tip there, which you can see, I've just applied some correction fluid to make it stick out a bit more. And here I've just used pieces of paper and glue. It goes down to 15 picofarad through to 100. I used a capacitance meter and the maximum is 450 picofarad. So the benefit of having the capacitance is that you can use the indication here, this is where you get the peak, as a form of inductance meter. So if you use this a lot, you'll learn certain rules, like 5 microhenry resonates with 100 picofarad on 7 megahertz. I've done previous videos on that. So you eventually can learn how to do mental calculations on this. But yeah, this is just a measurement of the capacitance. Up here is the unknown coil connections. You just press there and that connects. If we take a look inside, it would have been better if I used a smaller box, because ideally, especially if you want to measure inductors at high frequencies, you want the wiring to be very small. Anyway, all that collection of resistors you see in the middle of the screen, you can see at the top those 3 resistors, 3 of 150 ohm, that's for your 50 ohm dummy load, and that bigger collection down the bottom. They don't have to be that size, but that's the resistors I had. That was the collection to give you your 0.2 of an ohm combined. And the BNC socket you see on the right, that is where the signal from the transmitter comes in. And so you've got the unknown inductor wired across there. Here is your variable capacitor, and just soldered to that are the 2 diodes, 10 nanofarad ceramic capacitor, and just here is your 10 megohm resistor. And I've just got an alligator clip and a lead, and that goes to my multimeter. Positive, it's a voltage setting. You might initially try a maximum of 40 volts, then you'd go down to maybe 4 volts. And yep, so that's all there is to it. There's plenty of room. This is the back of the panel meter I mentioned. I might put a battery and a DC amplifier. That will make the unit self-contained, and having an analog meter, it will be a little bit quicker to do measurements than relying on a digital scale. So the idea with this is I'll have a 1 to 10 scale, and then I'll mark 7, and 7 is 70% of that. So it will be quicker and easier to get a peak and to make adjustments. But for now, I'm just going to demonstrate that the concept works with just a multimeter on voltage setting as the indicator. I've got 2 coils. One of them is much bigger in diameter than the other, whereas this one is on a narrower former but is longer. Let's first measure the inductance and then try and measure the Q. The thinner coil you see here is about 44 microhenry. The bigger coil here is just under 100. Describing this test setup, first of all we have the signal source, a HF transceiver, FT817 in this case. For the coils that I'm testing, I'll be using the 160 meter band, around 1.9 megahertz. It's a good idea to use the center of the band when you're doing tests. So if the transceiver operates from 3.5 to 4, then try 3.75. If it goes from 7 to 7.3, then try 7.150, because you do need to vary the frequency, and it's a good idea to go both up and below your center frequency. So pick somewhere in the middle of the band that your equipment transmits on. For bigger inductors, you use a lower frequency, smaller inductors a higher frequency. You could go up to 28, 50, maybe even higher megahertz, though I haven't tried it up there. Today I'll just be testing the 2 coils that I've just shown you. From the FT817, the signal goes into our Q meter. Finally, you can see the alligator clips there. This goes to a DC voltmeter. This happens after you've rectified the RF through the diodes, so it's now DC. And I've got it set on the 40 volt range, although you may want to drop it down to the 4 volt range, depending on the voltages you get. I've now plugged in the smaller coil, which is what I'm going to be testing first. What I'll do is I will apply RF. For that, I'll press the key, and then I will adjust the dial on here until you get to a capacitance setting that gives you maximum indication on the multimeter. With the digital display, it is quite touchy. Okay, at just over 150 picofarad, we've got a maximum reading of around 7.6 volts. Just to make sure I've got it exactly peaked, I will vary the frequency until I get a maximum reading. And we're at 1906, and we're getting 7.7 volts. So our center frequency is 1906 kilohertz. I'm getting 7.7 volts. Now what will happen is if we go away from the center frequency, that's our center frequency there, the output will drop. And we want to know where, let's call this 1, it's actually 7.7 volts, we want 0.7. So we need to calculate that. So 70% of that voltage is a critical point, and we need to work out, or we need to measure, what frequency this is. So this will be higher. Here's your center frequency, there's your lower frequency here, and from this you can work out the Q. Basically, the higher the Q, the closer in the lower and the upper frequencies are to the center, and vice versa. Low Q means that it's much shallower and they're further apart. We now need to calculate 0.7 of 7.7 volts. So 0.7 times 7.7 is 5.39 volts. So there at the top is 7.7 volts. Down here at the 70% level is 5.39 volts. We now need to apply transmit energy and move the frequency up, and take a note of our upper frequency where we're at 5.39 volts, and then we'll do the same for the lower frequency. Okay, we're pretty close now. We are at 1914. This is 1897. Lower frequency is 1897, upper frequency is 1914. The difference between them is 17 kilohertz. So we've got a 17 kilohertz span over here. What is the Q? The Q, as we said before, the smaller this number, the difference between the two frequencies, the higher the Q. Therefore, this number is going to be on the bottom here. It's, F upper minus F lower, which is 17 kilohertz. And up here, this is the center frequency, so that is 1906 kilohertz. This is where we get the calculator again. 1906 divided by 17, and according to this the Q is about 112. Although I've said this is a Q meter and not an inductance measuring device, you can actually measure inductance on this provided you apply formulas. As you can see here, we're on about 160 picofarad. We know the frequency, it was 1906. Now if you wanted to, you could make a spreadsheet, or you can find online frequency calculators. I've put in 160 picofarad there, 1.906 megahertz here. The result I get is 43.58 microhenry, which is pretty close to the 44 that I measured before. So yes, the Q meter does work quite effectively to also measure inductance, provided you've calibrated the capacitance scale okay and you've got an accurate frequency source. Next we'll try the bigger coil. Again, we set this to our center frequency of around 1.9 megahertz. Apply some power. Find a peak. Just adjust this to see if we can get a higher peak. Here at 14.6, we need to multiply that by 0.7. That's 10.22. We need to go up in frequency until we reach 10.22. We're pretty close here. And that's 1912. We'll now go down to 10.22 again. Near enough to 1902. So here we have a span of 10 kilohertz. Our center frequency is 1907. So 1907 divided by 10 is a Q of 190. When we look at our workings, we had 112 for this coil, and for this one here it was 190. So a significant difference in the Q of these two inductors. Sometimes it's important, sometimes it's not. If you're building a crystal set, for instance, Q is really important because it means that you are maximizing the signal strength in your headphones, in which case, if you had the space, you'd definitely have a coil like this rather than one like this. And there are factors that affect coil Q. For instance, the ratio between the diameter and the length. A long and skinny coil like this would have a inferior Q to one that's like this, where the length of the coil is pretty similar to the diameter, and that bears out in the measurements that we got. So it's quite nice that, you know, what you read about in theory does actually happen in practice. There's other factors as well. There's like, you know, the type of wire, the amount of spacing, all these other things can affect the Q of a coil, and for critical applications that's important. So to sum up, this is the little Q indicator that also doubles as an inductance measurer. All you need is a suitable transceiver that gives you a signal source and a suitable multimeter, digital voltmeter. But later on I want to modify this so I can use the panel meter. The idea I was thinking was that when you do your adjustments, you get a peak and you use this potentiometer just to set the reading to 1, 10, 100, whatever it is, full scale. So then you can adjust your frequency on your signal source. You can have a marker at 70%, and that makes it a bit quicker to do your measurements. You don't have to do so many calculations. You can just establish your kilohertz bandwidth and then have that divided by your center frequency, and that will give you the Q. So that's a little Q meter experiment. Never built one of these before, but it's a very useful instrument, and if you have tried them, or if you're inspired by this project to build one, then let me know how you go in the comments. And don't forget also, in the video description, I'll have some links to some circuits, other people's descriptions that might help in you building yours. Enjoy these videos? Want to start in amateur radio? Well, check out my books, Ham Radio Get Started for USA readers, and the Australian Ham Radio Handbook for those in Australia. For more information, visit my website VK3YE.com or search their titles on Amazon.